All right, y'all, this is Barry. I'm here today to talk about the Unit 3 notes for AP Physics. This is work and energy, also known as mechanical energy, and we will talk about power as well. And we're going to get right into it here. So first thing we need to talk about are the big ideas associated with this unit. First is big idea 3, the interactions of an object with another object can be described by forces. As mentioned in the dynamics unit previously, forces are going to follow us through everything that happens in AP Physics 1 the rest of the way because they are what drives motion, and that's what's really important for what we do in here. So kinematics, dynamics, going to follow us the rest of the way through here. Big idea 4 is interactions between systems can result in changes in those systems. And systems in particular are going to be really important here for our mechanical energy because, as you've probably heard in the past, energy is neither created nor destroyed. It just changes its form and moves potentially from one system to another. So looking at these different systems is going to be really important here. Big idea 5, changes that occur as a result of interactions are constrained by conservation laws. And again, to go back to energy never being created or destroyed, we're going to be looking at that right there, energy not being created or destroyed, just transferring between these different systems, and that is known as conservation of energy. So we're going to get to all those items. Please keep these in mind, and we'll revisit them at the very end. All right, the first thing to talk about today is work. Work is the transfer of energy that occurs when a force makes an object move. Okay, so in order to do work, we must have a force that's applied, and motion must be in the same direction as the applied force. And we see a young woman right here picking some books up off the ground. She's applying a force upwards to counteract that force of gravity that's pulling them down and moving them up some distance. We're going to revisit this as an example here soon. When we're calculating force, we need to know that force, when we're calculating work, we need to know that force and distance as they're being applied. So first we must know the average magnitude of the force and the direction of the force, and then the displacement. So the magnitude of that change in position and the direction of that change in position. Both these items are vectors, so that direction is important for each. And that's why it's important for each when looking at how they combine. When we calculate them, we're just going to have force times distance, force in newtons, distance in meters, or displacement, in meters. And then our work is going to be in joules. So capital J, joules are our new unit here for work. It is equivalent to a newton times a meter, given that we're multiplying force in newtons times meters and displacement there, okay? All right, now when we're doing work in a specific direction, it's really important that we look at the direction of motion. Okay, so any part of the force that does not act in the same direction as the motion that's occurring does no work on an object. And it says right here, this gentleman pushing the car, and asks, in what direction is this man working? And if we look, his shoulder, where this force is being applied from, is clearly higher than his hand, right? So we have some angled force application to the back of the car, even though the actual displacement is perfectly horizontal here. Okay, so we have some portion of this force actually pushing downwards, whereas it looks like most of it is likely pushing in the negative horizontal direction. We would need to find some way to determine the horizontal component of this force if we were to determine the work he was doing while pushing the car, because we can't use the entire force unless it's all in the given direction. That's really important, and we will revisit that coming up here soon too. All right, so our example here. This is Jessica. She's picking a book up off the floor, what looks like numerous books. Never said that English was my strength. Pushing up against gravity, she applies the force of 2 newtons and moves the book 1.5 meters higher. How much work did Jessica do on the book? So we would say 3 here and not just 3. Of course, we need to remember our bananas. We would say 3 joules of work are being done just by quickly multiplying 2 newtons times 1.5 meters. Now this really gets interesting when she starts carrying them across the room. Because now, as you see with our force vector there, she's still applying a force upwards to counteract that force of gravity that's pulling them down, but her distance is now moving in the horizontal direction as opposed to the vertical direction. So while the book is still resting in her hand, she moves it sideways to a position 0.5 meters away. How much work did Jessica do on the book? And if we look at our vectors, since they're in opposite directions, and we know for work to be done, they must be in the same direction. Per our definition of work in physics, no work is being done here, okay? Not on the books, at least. So potentially we could say that she's using some force to push her shoes there into the ground, and then friction force is moving her forward, and we could say there's some work being done for her to walk sideways. She is no longer doing work on the books. And that's important to note, okay? When we talked about our systems earlier, we want to make sure we focus in on those specific systems, and in this case, that system would be the books. That's what we're asking about. All right, now to come back to forces in two dimension here, as opposed to just pushing a car, we've got an image here of a woman pushing a lawnmower. So if a force is applied in more than one direction, as we see that force being applied down the handle of the lawnmower, the component of the force acting in the direction of movement must be found. We cannot use that entire force. It must be just the force component that's in the same direction as the displacement that's happening. So if Susie is pushing a lawnmower to the left, should this entire F be used to find the work she is doing? And spoiler alert, you've guessed by now, no, it cannot be used. We would need to find the X component, the horizontal component of the work being done here. And we would use that angle theta that's given there to do that, because that's the only force that's acting in the direction of motion of the mower. All right. Now, when calculating work, we need to look at positive and negative work. And that's what we're going to do here as we have someone doing a bench press. So during the ascent phase, ascent meaning moving upwards. So we're actually starting with that bottom image and then going to the top one there where the bench press has been done. This gentleman is starting with the bar on his chest and pushing upwards. The lifter exerts an average vertical force of 1,000 newtons against the barbell while the barbell moves 0.8 meters upward. We want to know how much work did the lifter do to the barbell. Okay, and we've got force times the distance, so this seems pretty obvious probably right away, right? The force is positive due to pushing upwards. The displacement is positive due to moving upwards. So we have both positive numbers. They're both moving in the upwards positive direction. So we're going to multiply our positive 1,000 newtons by positive 0.8 meters and get 800 joules of work being done for one bench press. Now, what really gets interesting is when we have to look at negative and positive work. Okay, so positive work is performed when the direction of the force and the direction of motion are the same. So this was the ascent phase in the bench press when they're putting it up. When we're throwing a baseball, when you're pushing upwards to jump, whenever those two directions match up, that's an example of when we're going to have positive work being done. Now, in the descent phase of the bench press, because that bar didn't get to that man's chest on its own, right? It had to go down from when he first lifted it up off the rack. So during the descent phase of a rep on the bench press, the lifter exerts an average vertical force of 1,000 newtons. It's the same bench, right? Against the barbell while the barbell moves 0.8 meters downward. Now, if we look at this one right here, we have a force of 1,000 newtons still being applied, but now we are moving downwards. So we have a displacement of negative 0.8 meters. So the force is positive due to pushing upwards, because that thing's not in free fall, right? Hopefully not. We don't want this person injured. But the displacement is negative due to the movement downwards. In this case, we have 1,000 times that negative 0.8, and we get negative 800 joules of work. And there's a couple ways that we can think about this, right? To say that a person is doing negative 800 joules of work is probably not a fully true statement, in that they are not losing anything from them as this work is being done, right? What we would say instead, and you see there on the bottom line, in this case, we could say that gravity is actually doing 800 joules of work during the descent phase, and the person does 800 joules of work to get it back up to the top. Gravity 800, person 800, one rep at a time. Okay, that's really what we're looking at there. All right. Now, before anybody asks or anybody has the question, no, that is not me. Mr. Barry does not wear jean shorts like that. I do not have a basement like this with these weird stairs in it. And yes, that computer in the background is probably older than most of you who are watching this. So just to get that out of the way, because I always get this question, it is not me walking up these steps. But we need to look at work performed climbing stairs. Reminder that work is force times distance. In this case, the force that we are overcoming is the force of gravity, is the weight of the person who's walking up the stairs. And every single time you have walked upstairs, you've done some amount of work. The force here is the subject weight. We would find that from the mass of the person. So we're going to assume here we have 65 kilograms, and thus we can multiply that times 9.8 meters per second squared and determine the actual weight of this person, something there like 640 newtons, somewhere around that. The displacement is going to be the height of each step. And note I said the height, not the width of each step. It's got to be the height, because our force that we're acting against here, and thus having to apply a force upwards with, is that force of gravity. So all we care about is the vertical distance being covered here. Okay, so the height of each step, typically about 8 inches or 20 centimeters. So if we look at the work done per step, here I used about 10, right, 9.8, so roughly 10 meters per second squared, and found 650 newtons times 0.2 meters. So we have 130 newtons times meters, or 130 joules of work being done for each step that we're going up here. We then multiply by the number of steps, and we're going to do a lab similar to this in class. Now, power. The difference here between between work and power is going to be the rate at which something is done. Now, here's an interesting way to think about this. If you were to walk around a lake or run around the lake, you are applying the same force for the same distance to move yourself forward as you go around that lake. And that might seem odd because if you were to actually go and do both those things, it would require more effort and what we would think of as doing more work to run than it would to walk, right? Now, what we would say for physics terms is your work is actually going to be the same, but the power that you're generating is going to be different. And again, power is the rate at which work is performed. So it measures how quickly work is done. Rate at which implies a measurement over time, so a reminder that velocity is the rate at which distance changes. So it's that change in distance over time. Same thing would be said for acceleration, right? It's the rate at which velocity changes. So to say rate at which just implies that we're dividing by the amount of time something takes. The same amount of work over a shorter time will produce a greater power. So the person running around the lake, or when you take that run around the lake, you're going to require more power to do that. You're going to generate more power in doing that than you would if you walked around it. Same force applied, same distance covered, but less amount of time means more power because you're going to be dividing by that, as we see right here. So power is going to be work divided by time, or P equals W over T. Power is going to be measured in watts. And you've potentially seen things like electrical power and how many kilowatts or kilowatt hours or things like that. We'll get to that when we get to electricity, but that is the same type thing here. It's the amount of power generated. Your electrical company probably misproperly labels that as your electrical energy, but that would be the kilowatt hours. Watts or kilowatts in general would be a measurement of power. Now, you might also see this as measured in horsepower, whereas 1 horsepower equals 746 watts. As you can tell right there, that's not a very helpful measurement given the 746, and we're definitely going to use our standard units here of watts. Now, remember that work is in joules, and T time will be in seconds in this case. So power in watts equals work in joules divided by time in seconds. Now, if we look at this also, we can see a couple things. First, reminder that work is force times distance. So W divided by T is the same as F times D divided by T. And we get into a case here where we are changing around some of the variables to see what else changes. And we've done a little bit of this with some of our other quantities here. But to look at this quickly, how would doubling the distance here, what I want you to do is I want you to pause real quick and think about these four and see if you can come up with what overall effect this would have. I'm gonna let you pause, think about that for a sec, and then we'll come back and we'll take a look at what does what. All right, now that you've paused and you've had a chance to come back to this, how would doubling the distance change the work? And so a reminder here, work up on top here is force times distance. So if we double this distance, we're gonna double the work. How would cutting the time in half affect the power? So I've got power here, work divided by time. Since time is on the bottom, a lower time will result in a greater power. So if we cut the time in half, we're dividing by half the value, and we would effectively double the power. How would doubling the time affect the work? And if we remember here, work is force times distance. That's a tricky one, isn't it? If work is force times distance, changing the time, it doesn't affect the work being done at all. Reminder, whether you run or walk around a lake, you're doing the same amount of work. The force and the distance are the same. And then how would doubling the weight affect the work? Weight is the force of gravity on something, right? And so we would have F here being doubled effectively. If the weight doubles, the force would double, and that would affect the work, which work is force times distance. That would double the work also, which really is to say it takes double the work to carry something that's twice the size or twice the weight, and hopefully that makes sense. All right, time to actually move on to energy. So we've looked at work, we've looked at power. It's time to think about how that affects energy. And since work was the change in energy, we're going to mention energy here as the capacity to do work. And they are very directly related, and that's why we talked about work first. There are many forms of energy. There's none created, none destroyed. It's only converted from one type to another. You could have chemical, sound, heat, nuclear, mechanical. These are all different forms of energy. We're going to look at mechanical energy most specifically in this class. Now that consists of kinetic and potential energy. Kinetic energy being energy due to motion, and potential energy being energy due to position or deformation, or really stored energy. Stored in something would be potential energy. All right, so first to look at energy and work, we've got our mechanical energy right there. It's associated with motion and the position of an object. It's the ability to cause change, whether it be change in position, change in velocity, change in the position located as far as how far things are above the ground, and thus the ability to fall due to gravity. These are all similar type things that we will expand upon in just a minute. It's going to be measured in joules. Jay, reminder there real quick. It is the same as work, but if putting work into something can cause a change in energy, then it makes sense that we have the same units here, okay? So keep that in mind, please. Joules are the units for both energy and work. All right, joule is a Newton times a meter we looked at earlier, force times distance. So same thing here. It might be found a little bit differently though. You see, because a Newton, right, if you remember from dynamics unit, newtons or force are mass times acceleration, which would be kilograms times meters per second squared. Well, if we plug meters per second squared or kilograms times meters per second squared there, and for newtons, we end up with kilograms times meters squared divided by seconds squared. All right, the first thing to look at here is kinetic energy. Kinetic energy is associated with motion of an object. It's often going to be referred to as KE, or potentially just capital K. Depends on the mass and velocity of an object, and our kinetic energy is going to be found by multiplying 1/2 times the mass times the velocity squared. If y'all were here in class right now, I would ask you what's going to have a bigger effect on the kinetic energy, mass or velocity, given this equation. And hopefully pretty quickly we see that velocity is squared, so it's going to have a change in velocity is going to have a much greater change in the kinetic energy than a change in the mass, because that value is squared. All right, so KE is considered a scalar quantity. Now, if it's a scalar quantity, what direction does it act in? And I'm hoping here real quick, your immediate response was scalar doesn't have a direction, only vectors have a direction, and that's correct. And that's because mass here is a scalar quantity, no direction associated with that. And when we take this velocity value and we square it, it effectively removes the direction associated with that as well. So because of that, we have no direction associated with this, and that's really important because we wouldn't say that any other type of energy necessarily has a direction associated with it either. And if all energies are going to be transferred from one type to another, we can't say that one has a direction and that one doesn't. Okay, so no direction associated with energy. Three different types here of kinetic energy. The first, vibrational, and this is due to vibrating motion. Things like atoms have vibrational motion. When we get to sounds and waves, we'll talk about vibrational motion. So we'll come back to that one a little bit later here, okay? Rotational motion, this is due to something that could rotate around, right? And that's rotational kinetic energy. And I say think back to centripetal motion and force. We're actually going to cover that coming up. So when we talk about things moving around in a circular pattern, we'll talk about the rotational kinetic energy associated with those as well. And then translational kinetic energy. This is energy associated with displacement. Something translates from one position to another. We get that delta X or that delta Y. This is what we're going to look at, right? Something actually moving from one spot to another. So we are going to talk about translational kinetic energy. A quick example here for us. You're going to find the kinetic energy of a 10-kilogram bowling ball that's rolling at 3 meters per second. We've got a mass, we've got a velocity. Pretty simply here, we're going to plug into our kinetic energy equation, and this should be pretty easy, right? 1/2 times 10 gives us 5. 3 squared is 9, so we should have 45 joules here of kinetic energy. And that's what this bowling ball would have if this guy wasn't standing in the bowling lane and most likely going to slip and fall down. All right, so some types of potential energy. So we've looked kind of at the basics for kinetic. We're going to look at the basics for potential now. 4 basic types we're going to take a look at. First is gravitational potential energy. This is potential energy due to the force of gravity acting on an object. It is known as the potential to fall. Okay? So something much higher up than something else is going to have a greater gravitational potential energy. We're going to expand upon that because that's the main one we're going to look at in this unit. We will look a little closer at some of these other ones as well, specifically elastic potential energy. So this is the potential energy of an object that is stretched or compressed. And as you know, in dynamics, we looked at springs, and shocks are really another type of spring. So something that has the ability to bounce back, to if stretched out, compress back in on itself, or if compressed in, to push back out on itself, something with a spring constant here. We'll look at how there is some potential stored in that quantity, and that's what makes it do this, really. Okay, and then chemical potential energy. A couple quick examples. Lots of things have chemical potential energy, but a couple quick examples here for us are food. There's stored energy transferred to people, right? They digest, break apart the ATP. That energy goes into a person and allows them to, talk, to watch notes, to think as they need to. So that's what one type of chemical potential energy. Another would be energy stored in wood, the ability to burn. Okay, would be a chemical potential energy. So it's the breaking of the bonds once a fire is started in wood that allows the release of light and the release of heat. And really, we just have a change there of that chemical potential energy stored within that wood to become light and to become thermal energy, which is heat. And that's really the transfer that you've got going on there. And then finally here, strain potential energy. This is going to be due to the deformation of an object. So if you have something that, like if I were to put in kinetic energy into bending a pipe, I put kinetic energy into that, I've moved it, that mass has some velocity, or at least a piece of it has some velocity to it, and I would be straining that object and then leaving it strained potentially, or bent to show that there's been a change in its potential energy. So that ability to bend, for a car to crack and crumple, those are all going to be types of strain potential energy, the ability to move and bend. All right, to look more closely at this creepy shelf and some gravitational potential energy here. This is, again, the stored energy in an object because of its height. So we see different objects here that are different heights above the ground, and they're each going to have a different gravitational potential energy. Now, it's not going to just be due to the height above the ground. The farther above the ground it is, the more stored energy it will have as far as gravity is concerned, but also the larger it is, the more massive it is. I shouldn't just say larger, right? Because we get back into our what's bigger, a pound of feathers or a pound of bricks. But one will be, we care about the mass here. That's before I get too far off on a tangent. We care about the mass of these different objects, and the more mass it has, the greater the potential to have this gravitational potential energy. So if we see here, down here, we have our gravitational potential energy. You might see GPE, or in this case, I just put PE. It's going to be equal to the mass times, because it's gravitational potential, our gravity constant, 9.8 meters per second squared, and the height above the ground that it is at. Now, to look at this real quick, changes in potential energy. If I were to change the potential energy of something, how could I do that? Right? If I'm doing it specifically without reducing the mass or increasing the mass, how could I do this overall? And I'm just going to end up changing the height. Okay? And if we think about the way a swing works, and we'll get a little more into this with our conservation of energy, the lower you are to the ground, the least amount of potential energy you will have, because you have the least ability to fall. The higher you are above the ground, over here on the left, the greater the gravitational potential energy that you will have, because you could fall a further distance, and that height is the distance that we're looking at here. We'll talk about what happens, but if you're thinking about this, you pause at that top point, right? So your kinetic energy is 0, and you're moving your fastest at the bottom point. So when the potential energy is its lowest, the kinetic energy will be at its highest. And we'll talk about that in just a minute here when we get to our conservation of energy. Our quick example here for gravitational potential energy includes one of the weirder pictures I've ever seen, but I find it entertaining for some reason, so we're going to throw it in there. This is Tanner's sun drop. It sits on a desk. For some reason, there's an iguana licking it, and it's 1 meter above the floor. The mass of the can is 0.5 kilograms. We're going to find the potential energy. Reminder that is mgh. Our mass is going to be 0.5 kilograms. Our gravitational acceleration, 9.8 or 9.81 meters per second squared, and our height there is 1 meter. That's going to give us 4.9 joules of potential energy. All right, Here we've got an example really of our swing, okay? And it doesn't look quite, exactly like what we were looking at before, but we've got a spot here where we're swinging from A to B to C to D and back and forth again, okay? And as we're doing that, we're going to have a transfer of energy. It's not leaving the system, even though the height is changing, and thus obviously our potential energy is changing. Okay, that's because the potential at any point plus the kinetic at any point is going to be the total mechanical energy at any point of this pendulum or of a person on a swing or anything like that. So if we look at point A, we've got our high potential and low, and really at some point there's zero kinetic energy, right? Because it's at its maximum height. As it moves from A to B, it's going to move faster. The kinetic energy is going to go up, and it's also falling down, right? To some degree, that height above the ground has decreased. So that potential from the highest point has transferred to kinetic until you get to the very bottom there where it would be at its maximum kinetic energy and its minimum potential energy. As it moves to C and begins to go back up again, it will slow down until eventually at D, it will pause for a brief instant again before coming back down again. So again, we just have a transfer of kinetic to potential and potential to kinetic and back and forth as a person swings here, right? And that would be assuming that we're not having any sort of friction in the swing or the pendulum or, air resistance or anything else that's slowing it down. If there was, and you were on a swing, this is why you need to kick your legs on a swing. In that case, you would be putting work into the system. And remember, work going into a system, in this case, you being on the swing, would increase the overall energy and allow you to keep going and potentially even reach a higher height and a faster velocity. So if you're pumping those legs, you might be going faster and faster as you keep going. If you stop moving your legs and you just set in the swing, eventually, due to friction and air resistance and things like that, you're going to end up resting at the bottom and not moving at all. Something maybe you didn't think this specifically about, but something you've been doing, I would say, since you were a kid and you were on a swing. All right, so we just kind of went through, I guess, an example of the conversion of kinetic to potential energy, but we'll use this one real quick too. We've got some sort of gymnast doing some tricks across the floor. And what they've got here is some interaction as they hit the ground and then bounce up, and we have a high velocity as they go up until we get up to that apogee when they have almost no velocity, and thus you see the kinetic energy going down until that maximum point. But because their height is going up, we get an increasing potential energy. And then this comes back down until we get another interaction with the ground. And so the combination of these two should give us a constant mechanical energy throughout here because it is conserved. It's just changing types as it goes through this graph. Now, an interesting thing to look at here is what happened here? Our total mechanical that was right here dropped down and became a lower total mechanical energy. And Barry, you said that energy cannot be created or destroyed. Where the heck did it go? Well, if we go back here real quick, and we remember that there is some strain potential also that could be associated with some sort of collision or some sort of interaction there, that's what's happening. You ever done anything like this? Then you felt an impact on the ground. And some amount of energy is lost as this person interacts here with the ground to bounce up and get moving, and here again to continue moving. And if you notice, that total height here is lower than the maximum height right there. And that's because some amount of energy was lost from the system as a whole. And again, not lost. I shouldn't say lost, should I? I should say it was transferred and moved into something different. An impact here as they hit this bed or this trampoline or whatever else it is to move continuously onwards. Now, if it was a full trampoline, there's a chance that this would become even higher over here because some amount of potential, elastic potential, something like that here could transfer to that system as well. So again, this is a long way of saying never created or destroyed, just transferring from one type to another. Okay, to expand further upon that strain potential energy that could be there in a trampoline because that's full of springs and that's what's going on. A strain potential energy would be something along the lines of what could happen with the spring. And we talked about springs just recently in our dynamics unit. And if you remember, the force applied by a spring is the spring constant, K, times X. It's displacement, it's overall stretch, right? Now, the amount of deformation is going to be a very similar type thing here, okay? So a greater deformation is going to have a greater strain energy here overall, and this is going to be based on that delta X, okay, how far something is stretched. And what this is to say here, if we have our rest position and we pull this out here, we apply a force to pull out the string and hold it right here. It now has the elastic potential to spring backwards, okay? has elastic potential to spring backwards. In the same way that the force applied isn't quite the same as the energy here, we're going to say it's not just kx in the negative direction, it's 1/2 kx squared. And that should look really familiar to our kinetic energy equation. Okay, so the strain energy, the strain and the stiffness associated with a spring, we can find how much energy is stored in an extended spring by saying it's 1/2 k, the spring constant, times the distance that it's been extended or compressed if we went the other direction, squared. 1/2 kx squared. Okay. Now we can see things like this in a fiberglass vaulting pole. If somebody was a pole vaulter, there's energy stored in that. As it bends, it springs back and pushes the person over. I have a couple redundant items here, so apologies for that. Or a person bungee jumping, as they go over the edge there is that strain energy, that potential, that elastic potential to come back in the bungee cord. Or if we see here this hockey stick that appears to be bent to some degree, well, it's made specifically to bend some and then flex back so that that shot is coming off there with a higher velocity than it otherwise would be. So some examples there of strain energy. All right, so to get to conservation of energy, this is really the end goal for this whole unit. Excuse me. Something that we need to think about here, again, the total energy between 2 points is going to be fully conserved. Okay, we have conservation of energy. We've talked about our potential energy types and our kinetic energy types, and we see that that's redundantly put on here twice. Okay, and so that's implying here that the initial potential energy plus the initial kinetic energy, the total energy at the beginning, is going to equal the final potential energy plus the final kinetic energy, the total energy at the end, right? And so conservative forces are going to allow this to happen. So things like gravity and electrical forces and all of this is going to allow for this conservation of energy. Now, if we were to lose energy from a system, again, it's not lost, it's transferred to something that would take it out of the system then. And that's things like friction or air resistance, right? If you rub your hands together, you're losing some amount of energy there because your hands are getting warmer. That thermal energy is energy lost after you have taken that stored chemical energy that you got from food, made it into your own potential energy, turned it into kinetic energy. The loss from your system then, and the reason we need to eat more food, is because you've changed it to thermal energy, okay? And that happens as you move throughout the day. And this is why you must replenish the energy in your body, i.e. you must eat food, all right? So a person here is pedaling up to this point, and right here we're going to assume that they stop pedaling, okay? And they have some kinetic energy then. And as they start going up, they're going to slow down until they get to the top, right? Assuming their kinetic energy was enough. So that kinetic energy here, as they get slower and slower and slower, is changing and going down until they pause for just a brief moment up here at the top. As they pause, that kinetic energy is going to be 0. But if you notice, their height went up. And so that gravitational potential energy has increased. So we've gone from kinetic energy in, to potential energy at the top. And then as they roll back down the other side here, this gravitational potential energy turns back into kinetic energy. The further down the hill they go, the faster they will go, because that gravitational potential energy will become kinetic energy, and they will be back at their maximum speed down here at the bottom. Now, obviously, this assumes no friction and no air resistance, as we have assumed in the past. An example here, we have a diver with some mass, m. They drop from a board that's 10 meters above the ground, and they find that the speed, that we want to find the speed, at 5 meters, halfway down, all right? Their kinetic energy here being 0, and we know that it's a 10-meter high dive. Now, I think if we take a moment just to ponder this, the quickest response here is going to be, well, we don't have enough information to figure this out, right? That seems odd. But if you think about this real quick, we're in a free fall scenario, right? And so we're not going to worry about the mass of the person, even though so far we've looked at the mass of these different systems. So I'm going to talk you through this one real quick. I'll give you a moment then to pause and try to work this out, and then we'll take a look at the answer, okay? So if we're up here at the top, we have no kinetic energy yet. The person has not begun to move. There is some potential energy that would be the mass of the person times our gravitational acceleration times the height here being 10 meters. As they go all the way down to the bottom, once we get right at that point of the surface of the water, we now have no height anymore, no height above the ground. So we would have no longer any gravitational potential energy, and we would end up being at our maximum velocity right before hitting the water, because all of our gravitational potential energy up here has become kinetic energy down here. Okay, we've had that transfer the whole way down. If we want to look in the middle point here, I could say, okay, my kinetic energy here of 0 plus my gravitational potential energy here equals the kinetic energy here plus the gravitational potential energy here in this location. Now, if I look at that, it's Ke plus Pe up at the top equals Ke plus Pe here in the middle. Well, Ke is 1/2 mv squared, and Pe is mgh. And that's going to be true in both locations. If the mass of the person doesn't change, does it matter what the mass is? Or can I just cancel it out of all of those quantities? So that's going to be your hint. mgh up here plus Ke up here, which is going to be 0, is going to equal mgh here plus 1/2 mv squared here, but we can ignore the mass quantity in each. So gh plus 0 equals gh plus 1/2 v squared at this 5-meter location. I'd love for you to pause real quick and see if you can find out what the velocity halfway through this fall is. All right, welcome back. We're going to look down here in our bottom left and see that velocity should be 9.9 meters per second. So hopefully that's what you got, or something close to that. We will do many more examples like this in class. Oh, and another one even right now. So we've got a skier, in this case, sliding down a frictionless slope. And I mean, honestly, this is one of the few applications that we could actually think that it might be pretty frictionless, right? You're going down on skis, on snow. It's about as close to frictionless as we could possibly get. What is the skier's speed at the bottom? So we would have a case where up here, again, we'd have mgh. We're going to make that assumption they're not quite moving yet. They get going from a stationary point. And down here at the bottom, they're at their lowest height. There's no more ability to fall down, so no more gravitational potential energy. So it will be all kinetic energy down here. So in this case, we would say potential energy at the start, no kinetic energy, equals kinetic energy at the bottom, no potential energy. So mgh equals 1/2 mv squared. Again, the m's will cancel out. It won't matter what the mass of the person is. You could have the skier going down, a big skier, a small skier, whatever it is. If there's no friction, it won't make a difference because there'll be no normal force and thus no frictional force. And so we'll just want to see what velocity they have. Now a note, this is sneaky, right? It doesn't matter how far you actually have to go. What matters here is just that change in vertical position, because gravity only acts in the vertical direction. So it could be 250-meter slope, it could be a 50-meter slope, it could be 1,000-meter long slope. As long as this length, as long as the height stays the same, it does not matter what the length of the slope actually is. Okay? So we'll give you a minute to try to calculate that. Again, we've gotten rid of our m's, so gh up here at the top with this height is going to equal 1/2 v squared, because we've gotten rid of our m there also at the bottom, and see if we can find out what that velocity is. All right, so now that you've paused and been able to find out that velocity, we're going to check again. We've got 28 meters per second down at the bottom here. Okay, so hopefully you got that. Again, if not, we're going to do more examples with this in class for sure. Okay, a quick reminder on springs and how these work. So a reminder that the force in a spring is our spring constant times the actual compression or extension of the spring, depending on what direction it's going here, and that's called Hooke's law. We did that just recently, so I just wanted to remind you of that so that we can look one more time at that spring potential being 1/2 kx squared. Now, the reason we're looking at this and we have the 1/2 is because we're going to end up doing an area under a curve as an applied force there, works on the displacement on the edge. And because we know that F equals kx based on this constant, that's why we could say that as F increases, the x, the distance that it's stretched increases. And really, we're just looking for the area under the curve there, as we've talked about with some other items in the past. So our PE, because of this correlation that we know already between force and position of displacement, our PE is going to be 1/2 kx squared. And so if we were to release then this spring, and there's a mass attached to the end, we could determine the velocity of the mass by saying 1/2 kx squared equals 1/2 mv squared, because this potential of the spring would be what would drive motion here, as opposed to gravitational potential. Okay, we'll get into examples for this as well. All right, so conservation in a pendulum. Again, I want to give you all a chance to give this a little bit of practice because I think that's really important with this unit. But point 2, right? We see points 1, 2, 3, and 4 on here, and you see the positions all at the bottom. What I would say is, can you determine what the values A, B, C, D, E, and F all are? All right, I would give that a shot yourself, but given that you have the total potential here, at the position 1, well, you really have the total potential energy and kinetic energy at all positions. This should be something that's not too difficult to calculate, given that all of the energy there would be potential at position 1 and so forth and so on. And this actually even gives you the mass of the pendulum, even though really you shouldn't need it because we can cancel that mass out all the way through. All right, so a little bit more practice for you there. We'll get into more of these as we get into class. And so a quick reminder of our big ideas, and hopefully these are things that you saw. Big idea 3 being the interaction of an object with another object can be described by forces. We saw a couple cases here where forces are driving this, force of gravity, the spring force, that's all going to be driving what's happening here. Interactions between systems can result in changes in those systems, and that's that moving of or transfer of energy from one type to another, right? We stretch that spring out, we let it go. We've got an interaction within a system, and so it's going to cause a change in that system. And the last one there, changes that occur as a result of interactions are constrained by conservation laws. Quick reminder, energy is never created or destroyed. Hopefully you saw these throughout here. We'll expand upon all of this in class.